there's not been major updates in the field, but I think it's something good to know. A lot of the things that I'm going to be talking about, it's good to know in general. And so the slides are not old, they're vintage, okay, or they're pre-pandemic. And I guess there was no title announced. I wasn't asked for a title, so I'm putting my title on, but that still doesn't give you much information. So if, it was, yeah, probably have to switch it on. So this is somewhat more good. God is talking to us. So this is a title which is probably explaining a little bit better what I'm going to be trying to talk about, and hopefully leave you with less confusion that the amount with which we started. Although an actual title is probably this one. Okay, so how the astrophysical uncertainties affect synergic searches, and in particular direct searches for dark matter. And it occurred to me at some point while I was preparing this talk for other purposes that the Milky Way is a galaxy close by, right? As opposed to a galaxy far away. And then I was going through the literature and I found that this is really the only literary thing that I share with my late father. It's probably the 3 central volume of this. It's the Foundation. And the history of the Foundation of Asimov, it's basically the history of Star Wars. That's inspired by that. Like a Roman Empire collapsing in a galaxy. It's heavily inspired by the structure of a falling empire. And I think the fact that they had to specify that it was a galaxy far away, it's because they want to say, no, it's not really Asimov thing, which is in the Milky Way. We're in a galaxy far away, okay? That's a bit... I read shit about it. Even Paul Krugman was extremely against it. If you read the books, it seems like it's an entirely different thing. I spent last summer reading all these books in English, because the first time I read them in Italian, and it's mesmerizing. It's it's a really good one. I strongly advise it. And somehow, probably this publisher didn't get the rights for the last book, the second, which is the last, it was the last to be written, so there's some editorial mismanaging. And so another thing that I thought it was good to break the ice, not that everybody needs it, but I see people that haven't seen in a swimming suit yesterday, so probably it's good to break the ice. It's that the origin of the Milky Way is something we should talk about, because when we talk about galaxy, you know, any galaxy, that's exactly, the word owes it to Milky Way. So we are in a land which was first colonized by the Greeks. And galaxy, our galaxy comes from the word galactos, which means milk. So it's Milky Way, but then galaxy comes exactly from the same word. So any other galaxy is basically the Milky Way, by extension is the same word. And I don't know if you know the legend, at least what the Western legend is about. There was this guy, this little kid over here, it's the same kid. So this little kid over here, this doesn't really work on the screen. This was the son of Zeus, of Jupiter, but he was generated by a relationship with, by an affair with a mortal. So Jupiter was extremely worried that he wouldn't get full divine powers. So he decided, in order to help they didn't figure out genetics and stuff very well at the time. So he thought just the only way to have full divine powers was to having been breastfed by his goddess wife, which is a bit of a bizarre idea. Like you have an affair and a child out of it, and you give it to your actual wife, which might be angry about it. So the kid was breastfed by Hera, and eventually he gained full powers, and the guy became known as Hercules. That's the guy. And but by the time he was breastfeeding by Hera, some of the milk spread out of the breast of Hera, and it stained the sky, because everything happened in the sky because they're gods, and that's the Milky Way. All right, so that's a little bit the origin of the Milky Way. That's not a scientific account, but it's and of course this is the Western, the Greek-Roman legend. There's plenty of legends around. The Chinese one is extremely interesting. They have one in the Maori land. It's very interesting. I suggest to check them around. So, about us, the origin of the Milky Way, we all know that galaxies grow from the original perturbations, and they collapse into gravitational potential wells that grow and attract the gas. Now, this is a generic picture, but the interesting thing that we know is that these perturbations wouldn't grow if there wasn't dark matter. It's very simple. They wouldn't grow the way they grow from redshift 1000 up to today. and we really don't know what the dark matter is, so that's why we're here trying to figure out what sort of an extension of the standard model, if any extension of the standard model at all, because primordial black holes are coming back into fashion. But anyhow, let's say that we believe it's something beyond the standard model, okay? Which doesn't really change the nature of the problem. Now, this seems to be a bit off the subject, but it really isn't, because the detail of the collapse of these structures on the many scales, they bring you to the distribution of dark matter within those gravitational potential wells. And if you're really interested in what is the abundance and what's the distribution of dark matter around the galaxy or close to us, that's important, because the way we model it comes from the way we understand the evolution of the gravitational potential wells in a cosmological context. Okay? And in fact, when I was a student, this was not possible, and I think I was a student a bit farther in the past than most of you. There were no simulation with gas. Everything that people did back when I was a student in 2004 and 2005, they simulated the power spectrum of the CMB well, they had something that was statistically compatible with the power spectrum. They collapsed the structure in pure gravitational interaction, dark matter only simulations. They got the structures out. They got more or less the N in the M over Z and well, over the evolution of Z, and that was fine. Now people can model the subgrid physics of the halo, so the gas, how the gas follows the gravitational collapse, and form pretty galaxy-looking galaxies. Okay? Now there's a lot of details to this, but this is important because when you think of a single halo, so a single density distribution or matter distribution within a single halo, you typically think of something that is monolithic, is something scaleless. There is one power law or possibly a broken power law that scales with the mass of the halo. Doesn't matter what, you just scale the radius of the halo and the mass will scale accordingly. And we use NFW or Einasto or whatever it is. You can call it however you want, no disrespect. It's basically a broken power law at some point that you fit, okay? And you can think of a host of ways to parameterize it. Now the interesting thing is also that the halo extends way beyond the visible part of the halo, beyond the galaxy. That's extremely well posed. Actually, if you perform a mental experiment, because the gas, it's collisional and the gas is dissipative, so it will dissipate and fall at the bottom of the potential well, whereas something dissipationless will not. So that's fairly nicely fitting with a mental image, even if you simulate it. But the important thing is that whenever we want to model, and in order to know the dark matter density around the Earth or in a galaxy, we fit whatever we know about the structure of the dark matter to one of these power laws, okay? And all the things that people have been taught in school, maybe some of you didn't, and that's good, about the crisis of the lambda CDM, the small scale problems, they come from the fact that people are sort of fossilized on this one halo shape, which was coming out of dark matter only simulations, okay? Now, over the past 5 to 10 years, there's been a lot of development, and the very interesting thing is that the shape of the profile, and if you want, let's still use a power law, but let's use a slope that might vary, and also like a breaking point of the power law that might vary, that strongly correlates with the ratio of the baryonic mass to the halo mass, okay? So there is not universal shape, and actually whether it's cuspy or core or even a double broken power law, actually there's good reasons to think that in the very center of the halo it breaks again, because the baryonic effects, the physics effect are very steep. It really correlates on how heavy the halo is, how many stars they form, a little bit the formation history, okay? So we sort of have to break mentally this monolithic image of one halo being a power law, okay? Now this might be of interest for you or not. It's something that I find interesting per se, beside what is the exact dark matter density around the Earth, okay? Which brings us to the problem, how does this all fit with what's the dark matter density around us here at 8 kiloparsec-ish from the galactic center, all right? This is not in scale, this is not a real picture of the Milky Way, okay? There's different methods to determine observationally the dark matter, not a priori, so everything I said is the theory image we have, then forget about it. we go into real space, we measure stars in different ways that I'm trying to summarize here, and then you determine the dark matter density around the Earth with different methods. I'm going to be explaining what the methods are here, but this is the observational situation in 2014, which is almost 10 years ago. And this is some of these measurements, determinations put on a vertical axis. There's nothing on a vertical axis, but...
What is the observation? How do they measure the dark matter?
I'm going to come to that. Okay. But important thing is that you might notice that there is a huge spread, right? Especially in the error bars. The central point, this is a linear scale, so the central points sort of gather around the central value, more or less, but the uncertainties are widely differing, okay? And that's because different methods adopt different way of quoting uncertainties, of estimating uncertainties, of writing the uncertainties in the paper. So one of the methods that people use is the local motion of stars. So you take a volume 100 parsec around the Earth, you measure the velocity of a certain population of stars vertically, okay, that's statistical, you know. And then you subtract the weight of the disk of stars, so you see the disk of stars, which is this yellow slab. You know the total weight because you know the vertical motion of stars. If you subtract the weight of the disk, if you're left with something, that something is dark matter, okay? Now, it's not as simple as I'm saying. You have to solve the Jeans equations under given approximations and given assumptions, but you're not making any assumption on even the existence of the dark matter. Neither the shape, neither whatever. It's just whether you're left with some positive number, there's something there. And it's a very local determination. And I like this very much because you don't have to have an assumption about not even the existence of something there, okay?
How well do you know the visible contribution?
Say it again?
So you subtract the visible contribution, right? So how well do you know that, right?
I'm going to come to that.
Okay.
However, this method, well, the short answer is very poorly. In fact, this method gives you very huge uncertainties, most of which are systematic, most of which show those very huge error bars. And it's also the reason why you simply cannot combine different determinations because the uncertainties are just not telling you the same story. So you can't combine a systematic with the statistics. Okay?
And sometimes you end up with negative when you subtract the visible.
The central value can be negative, but the uncertainties never go down to negative, so that's fine. Right? The thing is that if you go back to this slide, the thing I like is that at 1 or 2 error bars, and I'm not calling them sigmas because they're not all statistics, they're all compatible with 0, most of them, with the exception of this point by Piero and Riccardo because they only quote statistical uncertainties without inserting the systematics, but that's fine, I'm going to come to that. Okay? So all of these determinations are compatible with no dark matter around the solar system. Around means a volume 100 parsec, which back into Asimov view is basically at least the next 100,000 years of the history of humankind. It's the first 12 planets colonized according to Asimov, okay? It's a big sphere around us.
And
Yeah.
for statistics, you probably can't do better than the number of stars.
For statistics, I have the remaining of my talk, okay? So, yeah.
Also with Gaia data, we have huge...
That's going to be the last 5 minutes of my talk. But with Gaia data, you're going to be hearing way more interesting things from Mariangela. Okay? So if you're interested in this, please do go to Mariangela's talk because the stuff that her group is doing is way more interesting than what I'm doing. Probably less conclusive. No, I believe so. It's less conclusive, but it's way more interesting. Okay? I'm setting the 0 order. Mariangela is going to take you to space. Okay? So this method is the one that I prefer conceptually because you don't have to have any assumption on the dark matter density and stuff, but it's the one that practically gives you the worst results. So that's the one I don't adopt. Okay? So the other method that you probably know about is the rotation curve. The rotation curve is telling you, I'm assuming that the disk of stars is a disk. It's a disk which is not a solid disk, it's an onion ring disk. So every slab, every corona rotates at a different velocity. That velocity equates to the gravitational potential inside the slab, and therefore I can equate the centrifugal velocity, or if you want the tangential velocity, with the gravitational mass inside. So if I measure the tangential velocity at any point along the radius, given that the stellar population is the right one and the assumptions hold, I know the total gravitational potential at each point, and if I subtract the visible component at the point, that means the gravitational component of the gravitational potential of the visible component, I am left with the gravitational component of the dark matter. Okay? That's a little bit the rotation curve game, which doesn't work as well as we would like it to, like it's given like the perfect tool, and I'm going to be trying to come into that. But again, if you have the total gravitational component, which is the rotation curve, and if you have the visible part of the gravitational component that you obtain observationally, and I'm going to come to that with very well-defined statistical uncertainties, what you can do is that you can fit the missing component to one of these two power laws or any power law of your liking and get a distribution in the parameter space, which is typically the slope and the density. So these are the plots that you typically see when you take something of the kind, okay? Of course, now you're making the assumption, A, that dark matter is there, B, that it has a single solid shape throughout the galaxy. You're also assuming that it's spherical, but that's the best posed assumption. But there's a host of assumptions that are going in the fact that you can perform this game of the rotation curve that people don't usually tell you, okay? So it's a bit the Woody Allen movie, everything he always wanted to know about the rotation curves, but you never dared to ask. There's a lot of things that people are swiping under the carpet, and it starts becoming extremely annoying.
I can keep the axis very well, but where was Earth? Where would Earth be?
Earth, well, this is not no, this is the Milky Way. Earth is around here, 8 kiloparsec. And actually, I'm going to be showing that because also it's very well posed that, as I said, in the central part of the galaxies, the potential is dominated by the baryons. Because the density of dark matter is very high, but the total amount of mass is dominated by the stars, because gas is falling and it's forming stars. So you expect the potential being dominated by baryons, so you see a smaller effect. And there has been a long debate on whether there is evidence for dark matter within the solar circle or not. For a long time, James Binney was throwing out papers in the 2000s that there is no evidence for dark matter within the solar circle, and of course he always denied that, but the papers are out. So you can read whatever you want in those papers. So again, this is a sort of putting all the methods together. You have typically, okay, there is a color coding. I don't remember what the color coding is. You can read it in the paper, but the yellow ones, the one with the biggest error bars, are usually the local determinations. And I think, well, if I can see my or Maria's name, so these are certainly these global fitting methods, which carry a lot of problems conceptually, okay? And these ones I don't remember, but you can read the paper, okay? But the interesting thing is that all these numbers sort of go well together. They are compatible with zero, a few error bars, again, not sigmas, but they fit nicely. The problem is that if you want to use these determinations to do actual science, right? Because if you're mixing these things with LHC measurements or detect detection, and you know way better than me how well you calibrate your systems, this is definitely not comparable, okay? So that's why at some point, Miguel...
What is this band?
This band is the result of this paper, which is Benito, myself, and Alessandro Cuoco in 21.
Okay.
And it's a bit higher because it includes the Gaia data. The Gaia data and another determination. It includes the Gaia data in a bizarre way that people wouldn't expect, but it does include the Gaia data.
So I understand band.
One at a time?
So I just wanted to understand, so this is a fit to the whole thing, or like what is the band? What is the band?
The band I'm going to explain later, but it's the determination of the paper from which this picture comes out. That's why it's the gray band in this picture. It's not an average. You cannot perform an average. I want to state this very clearly, especially for those of you at home. Don't perform an average. Don't do it at home, okay? That's exactly what I'm advising against, okay? Well, my collaborator when we started all this, my main collaborator was Miguel Pato. He's Portuguese. He spent a lot of time in Germany and was pretty determined about the fact that this stuff could not be used altogether. I was also, but Miguel is way stricter than me. So we decided to unify the formalism and come to the point, can we really do something with a statistical meaning? Can we unify the data? Okay, so now I will go a little bit through the details. I'll try to keep it quick, but the important thing is that forget everything. We are going to be using the rotation curve methods, okay, but we're not going to be including any dark matter. Before getting to the dark matter part, we just want to see if the total gravitational potential of the Milky Way that we determine with the rotation of the disk of stars and gas fits with the visible component. Okay, now this is also, this has a meaning under the assumption that at any radius the stuff, the stars and the disk is in equilibrium with the gravitational potential well, and if this fails, everything fails, and also that the motion is circular, which is an assumption which is sort of under control. But it's important to keep this in mind. If you're doing that, if we're doing this game, the assumptions have to be fulfilled. And people don't usually tell you that. Beyond 4 kiloparsec, that's fine. Still, there's some caveats that I'll try and come to. So of course you need tracers for the total gravitational potential, and you talk about the disk of stars, but typically you don't use stars. They're sitting in the disk of stars, but they're gas clouds. Technically speaking, a star is a gas cloud, but they're somewhat looser gas clouds. They emit in different frequencies, 21 centimeters, H1 line. However, at different radii, at different distance from the galactic center, you have different type of tracers. Gaia offers some tracers that are stellar population. The end game, when we did all this, we didn't know, but the end game is that the mass of data is so consistent and it's so big that it changes relatively little the statistics, whatever tracer you're doing, okay? So we put together all the data that were existing at the time. We created a database that you can use, modify, put different sets inside. We did it with Gaia. People can do it by picking by hand their favorite data sets. Eventually, it doesn't really change the game. There's other uncertainties that change the game more than this. So the sheer volume of data and the fact that the data, that probably the physical nature of the problem is really that one, doesn't change if you change the data, which is good. So this is sort of the rotation curve that we get if we, at the time, if you put together all the data. And again, this is the observed gravitational potential. I'm just looking at the observed gravitational potential in the space of the circular velocity. You could choose to use something else, but this is an observational proxy because also we don't observe the circular velocity. We observe the tangential velocity with respect to us, so you have to reconstruct it, and this is going to carry a big uncertainty, okay? Now this is the total gravitational potential. Now you want to go to the visible gravitational potential. And how do you do it? Well, you have to observe the different components of the stars in the galaxy. So you don't really break the galaxy, but you know that gravitationally they belong to a potato in the center, to a disk, and then there is gas that is not really important dynamically in the Milky Way, but you can add it. So the question is, does the potential of the baryons equate the total gravitational potential? And of course, you don't observe the potential of the stars, you observe the stellar distribution in the Milky Way. So you have to start from a density, which has a shape and a normalization somewhere. I'm going to come to that. Have an uncertainty on the shape and the normalization, and then get the potential, okay? So the whole game is starting from the density, which you sort of may observe, to the potential that, and the circular velocity that you want to compare with the one that you observe.
Because I'm not part of it, so I can imagine the bulge is basically like the gas potential. What does it look like compared to like the disk and a bulge?
The gas?
Yeah, so your potential that you're
like gas.
I mean,
It's a thin disk of gas.
how is it?
It's a thin. It's a thin disk of gas. Actually, at some point around 4 kiloparsec, it even counter-rotates, but it's dynamically irrelevant.
Okay, so it's just a simple, uniform density.
It's modeled as a uniform density. It has some density alteration around the spiral arms. It's dynamically irrelevant. You have bigger problem than its shape, that it's in the conversion from the observed line to the CO, because sometimes you observe the CO lines and not the H1, and then you have to convert, and that error is even bigger than its own component. But eventually, if you compare it to the other components, it's really dynamically irrelevant. You probably have clusters in mind where the intracluster medium makes most of the baryonic mass, but in galaxies, typically the gas I wouldn't say it's completely negligible, not in all of galaxies, that would be an overstatement, and I don't know about it, but in the Milky Way, it's dynamically relevant.
So if you didn't include it, it wouldn't change the results?
We did not include it, and it doesn't really change the conclusions. It alters a lot. We did include it, and we also played the game. At some point, we freaked out, and we started playing this dumb game of switching off components randomly, or data sets randomly, to see what happened if people just made a random mistake, and we always got the same conclusions. Maybe numbers sometimes shifted a little bit, but the final conclusion was the same, okay? So I'm showing you really the nitty-gritty details, but the point I wanted to make in this is that when you have different components, so bulge, disk, and gas, you have to model two things. One is the spatial distribution, and the other is the normalization, okay? So if you want, the normalization will carry statistical uncertainty because you can weigh the stars relatively well, but the physical distribution, the topological distribution, is something way more complicated. Okay, so you have to go, this density function has normalization and a space part, you can factorize them, and you break the galaxy just by eye in these components. Of course, you have to make sure not to count stars double, etc., etc. It's a complicated game, but you end up, so, sorry, I screwed the joke, but anyhow, so you go to the bulge, and you want to count the bulge, and that's what Miguel and I did. Okay, there is a pretty good agreement in the community, but we thought there was a slight disagreement about what was the shape of the bulge. And so we started talking to the people we knew in the stellar community and said, look, well, you know, we know about this agreement that maybe the bulge has a bar, maybe it has a double bar, it's not clear which angle the bar of the bulge is pointing. So no. There's no disagreement. There's only one good model, and it's my groups. And then you call another astronomer and tell, yeah, of course, and it's my groups. And of course there's, I don't know, many groups in the game, so you end up with different shapes, with different possible shapes for the bulge. Now I'm not going to list all of them, I'm just going to be saying that this looks monodimensional, like one dimensional is not spherical. That R is a convolution of different axes. It's a fully tridimensional shape, there's many fully tridimensional shapes, and one thing is the shape. That's a systematic, I would call it. One thing is the normalization. The normalization, you can cope with it by using microlensing, so it's a very good technique. We performed a lot of tests. It's been accepted since then to use microlensing to weigh the stars toward the bulge. So, end of the game, you have something for the bulge that sort of works, but you carry the possibility of different morphologies. Yes?
The fact that the Milky Way has spiral arms, does that change anything?
No. We did test the spiral arms. You see, I have an answer for almost everything. We did test the spiral, well, not for the bulge because the spiral arms are out in the disk, so it's pretty much the same thing with the disk. The spiral arms are even estimated, so there is an alteration of velocity of below 20% in the vicinity of the spiral arm. So the stars will feel an attraction, so they will change their velocity. The velocity that you're measuring close to the spiral arms is something that is altered by 20% within a certain proximity, well, I'll call it impact factor from the spiral arm. And so if you're measuring stars that are close to spiral arms, you're altering the circular velocity, but typically these people are clever and they don't take stars which are too close to the spiral arms. If you then redistribute the matter on the total disk, it's not really going to be changing the total gravitational potential. So there's different ways in which the spiral arms could affect your measurement and determination, but again, their uncertainty effect disappears with respect to the ones that nobody tells you about, and I'm here for. Okay? So again, you have something which is the systematic of the disk, and you have the statistical normalization of the disk, which you can measure with surface brightness. So again, you have two terms for the density. One is statistical and one is systematic. Again, the gas, so this is what was being asked. You have different models for the gas that looks like a thin disk, and eventually it doesn't really play a role. Well, we included it, we played with the uncertainties and models, it really doesn't change the result, okay? So now, if you want to look at the different components in the plane that we were using, so this is the visible gravitational potential. That's the gravitational potential of the visible component seen in the circular velocity. And all the blue lines are the alternatives of the bulges. And all the green lines are the alternatives of the disks, and then you have two gas models, and you have to sum them square. The thing is that I'm definitely not advising anybody to take an average, because each one of these lines carries a statistical uncertainty. It comes from the normalization. That's well posed. But each one of these lines is alternative to the other, because they're systematics. So the blue lines are all different possible realization of the bulge, and we just don't know which one is the right one. I would never average them. You can use Bayesian approach and do some model weighing or model determination, but that's not what we did at the beginning. What we did at the, how much time do I have?
3 minutes.
Okay, that's fine. So the first thing we did at the beginning is that if you pick a combination of 3 of this, each one, you have to pick a combination of 3 to have the total, the gravitational potential of the Milky Way. And each combination of 3 is one possible morphology of the Milky Way, right? So rather than calling them models, we call these morphologies, like visible component morphologies. And we add n of them. So say the bulge is Greek letters, the disk is Latin letters, and the gas is numbers. So you might have alpha A1, then you have alpha B1, etc., etc., etc. And so what you obtain is this spread here. This is all the central values. Of course, each one of them carries a statistical uncertainty. And so this band here is the band of systematic uncertainties. Now, how do you cope with it if you want to either fit the dark matter or say, even if there is dark matter, is something that we did in a very simple way. Every time you pick a morphology, the others don't exist. Very simple. You pick one morphology at a time, each one is a possible realization. And so even before venturing into getting the dark matter profile, we asked ourselves the question, given the pre-existing Binney and company papers, is there any way that I can, and given the distribution of dark matters around the Milky Way, around the sun that you saw in those previous plots, is there a way that I can safely state that the gravitational potential of the Milky Way, the actual gravitational potential of the Milky Way around the solar circle fits with the visible one, okay? So we did by doing a 0 parameter fit of each individual morphology to the data of the gravitational potential. That's very simple. Nothing more than that.
So, how do you exactly get from the red unbent rotational curve to this baryonic bracketing in orbits?
So this is a function, and these are data. They're unbinned. We use different techniques. We used to sample this curve at each point of each data. So we obtain the function and its uncertainty at every radius of each data, or we bin the results. We tried a host of things, and the conclusion doesn't work, doesn't change.
Just because it looks a little bit low, but
That's exactly what you would expect, because this is the visible component. This is only the visible component. This is the total gravitational potential. That's what you want, that it looks low, because that means that it doesn't fit to the data, and so there is a missing component, okay? But again, don't ever take an answer by eye, because you just change your scale and you get a different result, and then the Higgs boson doesn't exist if you just look at the data by eye.
no, but you still can see that.
You still can see, but by eye, I would never say that there is a major discrepancy. If I had to take a decision by eye, I would say, fair enough. It's like I would look at biology papers, this is not even 2 sigmas. Come on, give me a break.
For theorists, this is definitely
Huh?
For theorists, this is definitely a discrepancy.
For a theory, this is a big discrepancy. But I mean, I don't trust my eyes. Let's put it this way, I don't trust my eyes. That's why we performed a fit. Yes.
What did you do? With the
Yeah, okay. This,
ratios, like here,
say it again?
with the mass to light ratios.
Not mass to light ratio. Whoever mentioned mass to light ratio? I never mentioned mass to light ratio. Huh? The normalization, for the bulge we're using microlensing. So you have a microlensing signal on target stars beyond the bulge by the stars along the line of sight. And so this gives you the normalization of the bulge, because of course that's also dependent on the stars along the line of sight, so it also depends on the disk, so the normalization is automatically adjusted, and we made sure that there's no problem with the uncertainties matrix and all this stuff. Okay, it was a lot of work. But for the bulges, for the bulge, the normalization and the uncertainty in the normalization that you're not seeing, I'm not quoting the statistical uncertainty here, is the microlensing. For the disk is the surface brightness of stars in the disk, okay? And then you combine the three together and you have a statistical uncertainty which is well posed because each one of them is a statistical uncertainty because it comes from an observation. So morphology by morphology, you have a well posed statistical uncertainty. Okay? What you're seeing on this plot is not the statistical uncertainty. What you're seeing on this plot is one reference morphology in black, just because we decided this was reference morphology. It's just for visualization purposes. And this blurred line is the convolution of all the central values of all the other alternative morphologies. This is not the data we're using for the fit. For the fit, what we're using is, say, the one reference morphology and its statistical uncertainty that you do not see here, that it gets folded together somehow in the fit. Okay? You can perform an unbinned fit or a bin fit. And we do it morphology by morphology. So at each radius, you will have a goodness of fit of this curve, the visible potential, to the data. That's it. Right? Do we agree on that? Is that clear?
For instance, the surface brightness, you measure the luminosity, no?
Say it again?
Let's take the surface brightness.
Yes.
You measure the luminosity.
Yes.
Then you have to convert it into a mass.
Absolutely.
And what do? I mean, you know the mass of the...
You have a spectral model for the stars and you convert it into mass. That's pretty universal. You can fold in the uncertainties.
Okay, so you're assuming...
There is an assumption we're using. Yeah, of course we're testing also different assumptions. Yeah, absolutely. We also perform different tests by using different. No, it's well posed, but this is before what we're doing. Okay, here we don't actively fit that. Okay, so we take that. Of course, we made a test that by using different assumptions for different groups that doesn't change the result. So this is for each morphology what you're seeing.
So the fact that you have all that so small radius, the red dots are so small, are not representative of the fact that you know that it's so red for such small radius. No?
This is just shown for visualization purposes. We don't, and I'm going to come to that if I have the time, we don't include the data below 2.5 kiloparsec, if that's your worry, for very good reasons that are not only experimental but also conceptual, and I'm going to be coming to that. We do include the mass, of course, although the volume is small, so even if we didn't include the mass in the central 2.5 kiloparsec, it wouldn't really change the conclusions. But the discrepancy that you're seeing here is very small because the visible component makes most of the mass in internal regions. So the question that we're asking is, if you integrated it up to the radius of the sun, does the weight of the visible component fit with the perceived weight by the sun and its sisters around? And this is something that by eye, it looks like it's not the case. If you perform a parameterless fit, and you take the goodness of fit, this is exactly what you see. So for each individual morphology, so each one of these lies in one individual morphology, so it's a parameterless fit. This is the chi-square per degree of freedom. This is the 5 sigma equivalent, integrated from 2.5 up to whatever radius you point your finger on. So for each one of these individual morphologies, the chi-square per degree of freedom goes very bad, worse than 5 sigma, before the solar circle. But we're not including any dark matter. We're just asking the question, does this work or not? Does the visible component and the observed component fit or not? And the answer is not, and by far. Okay? We're not including anything else than the stuff that we know is there. Okay? Now, whether the circular velocity really represents the total gravitational potential, that's a different question. But if you're assuming that the circular velocity does represent the gravitational potential, well, then you have an answer. You can't match the total mass with the mass of the stars in the disk and the gas in the disk within the solar circle. Okay? And outside it gets very worse. The reason why this saturates, whereas you would expect to go worse and worse because there is more dark matter, is that the data are bad, so the chi-square per degree of freedom flattens down. Okay? Ruben, you had a question?
It's okay.
Okay.
Below 2.5, there is no way to do anything? 2.5 is the maximum. 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 2.5 is the max
Below 2.5, if I have 5 minutes at the end, I'm going to be telling you, but the answer is I don't like it. I don't like what happens, and it leaves me very disappointed. Okay? So at this point, only after playing this game, at this point say, okay, then on the top of each morphology, we will add a dark matter component. Okay? But it's only at this point. And at this point, you can add a dark matter component, which is the game we played before, and then feed it to the data and say, what is the parameter that fits it best? You like generalized NFW, you like an ASTO, blah, blah, blah. Now, this is the curves that you get every time you have a morphology, right? So every time you have a morphology, you take a dark matter profile with its own parameters, and you will get a blob like this. But if you have different morphologies and you don't want to mix them for some reason which is fairly well posed, so you have different morphologies and you fit each one of them to the data, and these are only 5 without showing the uncertainties, you will get something like this. Okay? So each blob is the 2 sigma of one of the morphologies. And as you can see, you get a sort of spread, like a decent spread in the density, although that doesn't really change too much. But the variation in the slope is wild. So if you're really interested in the local dark matter density and you assume you can fit everything to one slopey component, that's fine. You have a spread which is not really too bad, but if you're interested in something toward the galactic center, you really care about the slope, that's a mess. Okay? There is another question. I'm using an instrument which turns out to be relatively precise, but is it accurate? Right? So that's something they teach in the first year and most people tend to forget, probably not in the lab, but theorists do. So I always have this problem that I can measure my fever down to 0.2 Celsius, but then sometimes the thermometer is screwed up. And so we performed a lot of tests. Actually, one of the authors is currently at the beach, I believe. Is she at the beach? Okay. And one of the things that we did is to test with fake data whether it's reliable and accurate or not. And the answer is that there is remarkable accuracy on the local dark matter density, but the accuracy on the slope is very bad. So not only this approach will give you results that vary with the slope, so you cannot really tell what the slope is, and in any case the result you get is off by the physical reality. So forget the slope. So if you want to extrapolate something to the galactic center, which in any case I do not recommend, I don't recommend to extrapolate these results toward the galactic center, but if you do, you have a double problem that first of all the slope variation really depends on your observed distribution of stars. Second, the instrument is not accurate. So whatever you're doing, which is something I do not recommend for several reasons, it's even wrong, very likely. Okay? So what is it that you do?
The certainty, it seems that also like RS is, well, not well constrained, right? So is the uncertainty on the slope connected?
Yeah.
You put the
Absolutely. You can trade one for the other, they're degenerate, and so, yeah.
But do you assume cosmological mass concentration relation in this data?
That breaks down. If you have scale radius and slope, you don't need the concentration. Like it's either scale radius or concentration is one of the
No,
right.
no, what I meant is a prior that connects RS and rho naught, for instance.
You have 3 parameters, and you can trade one for the other. So if you have scale radius, you don't need to use the concentration if you're using scale radius, slope, and...
Yeah, probably I'm just talking about that from embodied simulation.
No, we don't use any prior.
Yeah.
Your question is, do I use a prior? No, we don't use any prior. No. Well, we're using a prior on the scale radius, which you can transform in a prior on the concentration, which is so big that doesn't affect the results. Okay? Sorry, I didn't understand the question. So what is it that you do? Well, there is well, let me see if I have slides. No, I cut a slide which was extremely important. And this is the fact that all of this is given by the fact that we are... So this is the galactic center. We are should we paint the Earth blue or green or brown as it has become recently? Probably blue. Okay, so we're here, and then you're observing the stars here. And so the star is going around the galactic center with a tangential velocity, but we're observing this component. Okay, right? So if we wanna re-put it in the reference frame of the galactic center, we need to know our velocity with respect to the galactic center and our distance with respect to the galactic center if we want to reconstruct this, okay? If we want to reconstruct this from this, okay? So we basically need to know our own distance from the galactic center and our velocity with respect to the galactic center if we really want to transform our observations into the actual thing with respect to the galactic center. And the thing is that these two things are known with uncertainties, okay? And when you fold those uncertainties in, well, what I showed you was all for given R0 and V0, but when you fold these uncertainties in, then your uncertainties blow up again. Because on the top of all the distribution given the morphologies, you will have to fold in the uncertainties on ρ0 and V0, okay? So that's some work that we did along other things with my former student Maria, and this is something that we had back in the first paper that we had on this, in which we marginalized over all the uncertainties by fixing the radius and profiling over, fixing R0 and profiling over V0, or fixing V0 and profiling over R0. Then there was a gravity determination of R0, which was very tight. The uncertainties were very tight. That doesn't really change the uncertainties, but the conclusions. But if you're interested in the spread of R0, that's more or less what you get, okay? And one thing that I would like, it came out in a conversation yesterday, this is the value that people usually quote of 0.3. It's outside the 2 sigma region, okay? Now, if you're comparing experiment by experiment and you all fix them to 0.3, that's fine, because you're all comparing things. But if you want to do science, that's definitely not a good result. So one thing that Maria did was, because she's really hacky and geeky, she put the full likelihood on this, on this website. It's published in a paper. We strongly advise to use it. We have a case example of how to use it. There's more than one. Giovanni, you were in the second paper where we used this, right? For a specific approach. It can be used, and we strongly advise to use it, because eventually, including the full uncertainties, it does change your results, okay? I don't know how much time I still have, but 15. Okay, so I can show you some of the results. Yes?
It seems that like the uncertainty due to these are not is bigger than the one given by the morphology.
Okay, I don't remember if this includes profiling over the morphologies with some technique that allows you to do that.
Oh, okay.
Some sort of Bayesian technique that my Bayesian gurus tell me that it's not a sin. Okay? I don't remember exactly what this is, but we spent a lot of time thinking about it. So I might actually have to read the paper again to tell you what we did with this, but I think this folds in the uncertainties from the morphologies, okay? But as you might tell, this is a factor too. Okay, so one other thing, this actually is an answer to your question. Here we're using Gaia data. They quote 2 systematics, 2% systematic versus 5% systematic. We're using Gaia data for the rotation curve, not for other things, okay? And it's remarkable because Gaia is sort of blind beyond a certain distance from the Earth. It's not super good. So the rotation curve that you take from Gaia is limited for something from 5 kiloparsec to 11-ish or 12-ish. And still the results are very much compatible with the rotation curve that we get that extends farther away. But again, this is to stress the point that the results are very, very, very much compatible. Doesn't matter what you do with the data are really telling you that. So it's something that stresses me less than other things. But again, there is a factor 100%. This is 100%, which is a lot. Okay? And we're talking about the zero order system, the zero order term, right? So whenever you want to play this game of putting things together, and especially if you're interested in the direct detection, as you know better than I do, this term that I'm telling you here is even the most stupid one, because you have the phase space distribution that I'm not even touching, and then probably Mariangela is going to be hinting about. But the fact that even the zero order term is so wobbly, I mean, you can assess the uncertainties well, but then the answer is non-conclusive, like you have a factor 2, okay? Like it or not. For an astrophysicist, that's very well posed. I mean, I remember Paolo Salucci saying, oh, then I'm giving you this number, but I don't care about this number. It's just the density here, it's whatever. And if it's a factor 3, for me it's fine. Which, from an astrophysicist point of view, is very well posed, okay? Is this, no? Okay. Okay. Okay, this is again this slide. Okay, the point that I wanted to make here is that when you scan over all possible morphologies and you have these slopes that change, then you might be asking yourself whether this spread in the astrophysical quantities really affects the data. And here I'm showing the delta in the local density, but also this is the delta J factor for annihilation in the galactic center, if you care about it. And this is the delta in the density, in the dark matter density around the Earth. And as you can see, it's a factor 2, as I was showing you before. So this thing really affects, these uncertainties really affect your results, the interpretation of your results. This was something that we showed. Now we're varying R0 and V0. So the galactic parameters that are determined astrophysically, and this is how, this was the lux, the 215 lux limits, how they change, how the interpretation of the results change if you only change R0 and V0, and you propagate that into the local dark matter dimension. So as you can tell, that changes quite a bit. Okay, I mean, most of these papers were in between 2015 and 2018, so we applied just the astrophysical uncertainties to the interpretation of the direct and indirect results to a specific model, which in this case was the singlet scalar, just to show how you go from the astrophysical uncertainties to uncertainties in the parameter space in a very simple model, where especially the direct detection is just the coupling to the Higgs, so it's very simple. And you know, these are the constraints that you have on the singlet scalar, and you have to be along the line to respect the cosmological parameters, and this is the Lux limits at the time. And this is the direct detection limits if you're taking one R0 value, just dry, without uncertainty, okay? And then you move on and you say, okay, this is the same results, but I'm changing just the statistical uncertainty given to the morphology. Can you see a double shade of green? Very good. Very good. So the statistical uncertainties don't really matter, okay? You cannot see much, okay? But then you change the galactic parameters and this thing blows up. And you change the morphology and this thing is bad. It doesn't blow up, but it's bad.
So what does Lux use in their papers?
I don't remember.
Old one.
This is 2015. This is just a case study. I mean,
This is the old one, so we haven't updated in like 20 years.
But we're not criticizing Lux. We're just saying, look, if you're taking a central value, this is what happens when you include all the uncertainties. So the whole point of this exercise was to show theorists that if you take uncertainties from the astro world, this will go in your parameter space. The whole thing was to have a plot in which you had a mass and a coupling so the theorist could understand it. Okay. Again, this is how if you decide to interpret the galactic center excess, yes.
Sorry, could you go back to the slide?
Yes.
So here the dark blue, the lighter blue is the one that they use, and the dark blue is the one that you change?
This is the one. No, this is the one that we took for a central R0. I don't remember the detail. I can take the paper right after and tell you. But this was a central value that we picked for ourselves. We picked our morphology and we showed and we rescaled the Lux limit. And then we are applying the statistical uncertainty on that rho naught just by the data, but fixing R0 and V0. This is this, so it doesn't really change your parameter determination. And then if you vary the morphology, so you have that spread given to the fact that you don't really know the morphology of stars, that's what you get. But then if you vary R0, V0 with the parameters of this at the time of this paper, this is the blow up that you get because you get a big... this is the two envelopes, like these are the extremes.
Now it's going to be much better, the galactic one, no?
No, this is not a trivial statement. There is a better determination of R naught, so actually this narrows a little bit down, but the assumption that Gaia is perfecting the parameters is non-trivial, okay? It has done better, but it is non-trivial, okay?
Is it obvious in the electric spread if the spread is being dominated by uncertainties on the density or the velocity?
It's not trivial, but it's reasonable to assume it, because when you change R naught and V naught, you're changing the circular, you measure this.
No, sorry. Let me restate the question. Is it one or the other that's dominating, or both uncertainties coming in?
No, both uncertainties are coming in. This is just, so I'm sorry, I put one thing first and the other second. This is coming before that curve that I showed you where we're factoring in everything. But now we're factoring out here, we're showing only the uncertainties due to the galactic parameters in the case of the maximum envelope variation, and here we're showing under the morphology, but the two things come inside. Okay, and there's one thing, just I'm gonna come to you. As time goes by, this is narrowing down, but even the morphologies are narrowing down because some realization of the bulge are being ruled out by different observations. Not really, because Gaia at the moment can't really see toward the galactic center, but you're sort of narrowing down things. So this is getting better, but slowly, and it's a matter of taste whether you should go in one direction, like perfecting the R naught, B naught determination or not. Still, this dominates. The galactic uncertainties dominate way more.
And both R naught and V naught, they go into rho naught, is that?
Yes, everything is going into rho naught.
Okay.
Everything is going
That's
to.
what the changes.
Yeah, exactly. This was that was that sort of marginalized curve that we were showing, testing different profiling over R naught and V naught or different type of data. Okay, this is how the galactic center preferred region if you decide to interpret the gamma ray excess toward the galactic center in terms of singlet scalar model, which I don't suggest to do, but this is what would happen to the favorite region if you take into account the morphology. Actually, this blows away because gamma blows away. And so the density in the galactic center, and this changes by orders of magnitude where the favorite region is, so it might be ruled out or not by existing data because you're changing your interpretation based on the fact that you're changing the morphology of the stars, and so what is the galactic density, what's the dark matter density in the galactic center, given to the fact that you have to adjust it to the gravitational potential of the galaxy. Okay? So, long story short, it really impacts your results. It doesn't look like, but the astrophysical uncertainties, which are sort of trivial, impact your interpretation of the physics. And I would find it a bit embarrassing if we were saying, well, we found dark matter, but not because we forgot to include changing the reference frame between ourselves and the galactic center. You know, yes, it's the first year. You should take that into account. Okay.
Are we ruled out by direct detection?
The resonance is not.
I should plot this plot into here, and sort of is. But the whole point is not whether it's ruled out or not. It's how the region moves. And this is a very simple, we did this in a very simple model because you basically can see by eye the terms and the physics. But if you go in a more complicated scenario, this thing will play non-trivially and where the parameters couple. So our point is, do use it in your scenarios. And this is a sort of wimpish, but if you do it in other scenarios, that's more complicated. So the whole point was, this was before we published the full likelihood. So the full likelihood, we republished in 2019, so it includes, or 20, so it includes a lot of things. It's very accurate. Ruben, you had a question? Do I still have 5 minutes or not?
5 minutes, yeah.
That's good.
The bells will ring.
Huh?
The bells will ring.
Oh. It's true. God will talk to me. So this is probably to answer Thomas' question, right? How about the galactic center? So we cut out everything in the central 2.53 kiloparsec for a lot of good reasons. First of all, you don't measure very well the circular velocities there. Second, you are not even sure that the stars or your tracers are following the gravitational potential. So even if you were able to measure the circular velocity, it might just be following some strange eruption or bubbling Hell's Kitchen stuff. Third, the potential might not be, it is not spherically symmetric. Actually, there is a strong asymmetry. And there's another point that I forget on the tip of my tongue, but there's a lot of good reasons to say you can't play the rotation curve game in the central region of the galaxy. So on the one hand, I would not trust the results. On the second hand, I would not necessarily extrapolate the results outside toward the galactic center, because you see evidence in numerical simulations that the density might bend again because there's a lot of activity and the assumptions break and there is not adiabatic contraction, a lot of things. So what you do is that what you can do is to take stars around the galactic center, measure their motion, invert the Jeans equation, so just determine the total amount of mass by Jeans equation inversion. So you don't use the rotation curve, but you can estimate the total potential. And then you estimate the stellar mass with microlensing, subtract the two, and say, is there any dark matter there? And you completely detach the problem from what happens outside. Which is also relatively well posed because the amount of mass in that region is small, so if you make a relatively big mistake there, it doesn't affect outside. Okay? I'm done. So, what is it that we have here? This is the total mass, okay, for different morphologies of the bulge. And this is the dark matter mass that you obtain by playing this game, and I think this is a 1 sigma band. Okay? So whatever conclusion you want to take from this game is inconclusive about the total amount of mass in the galactic center, because the amount of dark matter mass in the central cube of 3 kiloparsec-ish, because it's very close to 0, and it's definitely 0 at 2 sigma. And we expect that, because we expect the gravitational potential to be dominated by stars, because gas cools down, it falls into the galactic center. There was a paper from Dan that inspired this. And if you decide on the top of it to model the amount of mass as the integral of a spherical density, which for the dark matter is sort of okay, and then to convert it into parameters, you have something like this, where I made a big mistake because I decided to flip the colors, so now I don't remember which one is forbidden. And Maria told me. I mean, it's one of the few times that she told me something very sensible, and I didn't listen. Oh, we wrote it down. Yeah. Okay. So as you can tell, only extremely dense and extremely massive regions are excluded, but basically everything is allowed. Okay, so the answers about what is the dark matter density or profile in the galactic center is completely inconclusive. And I think Maria was particularly enraged by a paper from some astronomers that were extrapolating whatever rotation curve between 6 and 10 kiloparsec toward the galactic center and saying, there is a core of dark matter in the galactic center, and she has very hot blood. She's from saying, oh, this is not true, whatever, da. So what she did was to extrapolate by continuity our own profiles, which is something I do not recommend to do. Said, but if we extrapolate our profiles toward the galactic center, this is what you get, which I don't think it's the real thing, but opposing to that paper is like, if you do it properly, what you have done, which I don't think is right, still you don't get a core, you get something around here, which is a sort of well-posed Navarro-Franken-White. But still, I don't recommend to use this determination. This was just because she wanted to prove the point that you cannot state that there is either a core or a cusp in the galactic center. Because this red dot is the extrapolation of an external profile toward the galactic center, and I don't recommend to do it, okay? Now, since God was talking, I think we should come to an end, and I will leave you with some conclusions. One conclusion is that you can definitely determine the local dark matter density up to factor 2, even if you factor in, well, first of all, there's a lot of uncertainties, galactic uncertainties, morphologies on the stars, but many of them have a statistical, you can put them under control statistically, which is satisfying. It's not non-trivial. You can sort of tame together the systematic uncertainties and come to the point that I would claim with confidence that probably a factor 2 about the local dark matter density is a reasonable uncertainty, so between 0.4 and 0.5, I mean 0.8, which is still non-trivial statement. Forget about determining the slope with a good uncertainties, with good control. So you can do whatever you want, but just be honest and say that it's not a slopey or chorey or whatever. Even not in the galactic center, around the bulk of the Milky Way, the slope is relatively unknown. And in the galactic center, there's nothing in God's grace that can tell you what the dark matter density is. So again, you can use whatever you want. It doesn't violate heavily gravitational constraints, but you can't claim something. It's just inconclusive, okay? And it's very depressing. But for better stuff and way more exciting stuff, go to Mariangela's talk. I'll try to be here. And I'm done with my part.